Hi everyone, my name is Tatiana Zemskova, and together with Alexey Staroverov, I will present our work, OVSegDT, a transformer-based approach for open vocabulary object navigation for mobile robots. We are research scientists at Cognitive AI System Labs, and here you can see our contacts. Let's start with the task description. In object goal navigation, an embodied agent is placed in an unfamiliar indoor environment and receives a target object described by text, for example, chair or plant. The agent must explore, recognize the target, navigate close to it, and stop, using only partial observations. In this work, we focus on open vocabulary object navigation. Here, the target can belong to an arbitrary category, including categories not seen during training. HM3D-01 evaluates this with seen categories, synonyms, and categories that were unseen during the training process, making it closer to real-world use. The challenge is to have robust navigation to all types of categories. Now I will describe our method, OVSegDT. OVSegDT is a lightweight 130 million parameter transformer architecture. The key idea is to give the policy a binary target mask as an additional observation. This mask grounds the text goal in the current image and provides special cues about the target location. On HM3D-01, OVSegDT reached a 44% success rate and 20% SPA on unseen categories, using only RGB input and no depth audiometry or large vision language planning model. This slide shows the architecture. We encode the RGB image and goal text with frozen CGLIP encoders, and also encode the previous action and binary goal mask. These embeddings are concatenated into one observation vector. A decoder-only transformer receives the last 100 observations and predicts the next action. During training, a critic head and a segmentation head help the model learn both navigation and target mask prediction.
Now I will talk about the EALM training objective. The main idea is to avoid a manually chosen switch from imitation learning to reinforcement learning. For each mini batch, we compute the entropy of the policy action distribution. High entropy means that the policy is still uncertain, so it should rely more on behavioral cloning. Low entropy means that the policy is more confident, so we can rely more on PPO. We smooth this entropy with an exponential moving average and then map it to a mixing coefficient between two bounds. This coefficient defines the PPO weight. The behavioral cloning weight is simply 1 minus this value. So the final policy loss is a weighted sum of PPO and behavioral cloning losses. This slide shows why EALM is important in practice. A gradual transition from behavioral cloning to PPO improves both training stability and sample efficiency. Compared with the JAG-RL baseline, EALM reaches better performance and reduces sample complexity by about 33%. We also compare it with fixed alternatives, pure PPO, pure Dagger, and combined Dagger plus PPO and early switcher. The key component is that manual switching is fragile, while EALM adapts the balance automatically using the policy entropy. As a result, the policy converges more smoothly and reduces collisions. Next, I will discuss active perceptions, which becomes important when we move from ground truth simulator masks to predicted masks from an open vocabulary segmentation model. In a realistic setup, ground truth segmentation is not available, so we use YOLO-YE to predict the binary target mask from RGB and the text category. Predicted masks cause a performance drop because the detector can miss distant or occluded objects or produce false positive. We address this with per category confidence calibration and fine-tuning of OVSegDT with predicted masks. During fine-tuning, the semantic reward encourages the agent to increase the visible area of the true target object. This acts as an active perception signal. The agent learns actions that make the target easier to observe and segment. Here are qualitative examples of OVSegDT navigation. Compared with the baseline without target masks, our method better recognizes when the target appears and switches from exploration to goal-directed navigation. The binary masks gives direct visual grounding and helps the agent avoid passing by the target or stopping at the wrong object. We conduct demonstration experiments on a real iRobot Create 3 robot equipped with a ZX camera, LiDAR, and an NVIDIA Jetson Orin PC. The robot successfully performs object goal navigation with categories such as white box or clothes. The navigation system demonstrates robust long horizon behavior, including effective obstacle avoidance during a movement through complex environments. To summarize, open vocabulary navigation requires accurate target recognition under partially observation. OVSegDT shows that a lightweight transformer policy can generalize to unseen categories using binary target masks and segmentation-aware objectives. EALM stabilizes training by removing the manual switch between imitation and reinforcement learning. Finally, predicted segmentation adaptation makes the approach practical beyond simulator masks.
The main direction for future work includes the adaptation of the method to complex text queries that require contextual understanding, for example, a mug on the kitchen table. Thank you for your attention.